Welcome to our deep dive into sphere packing.
Sphere packing.
Yeah, we're going to be looking at the history of this math problem
Oh, cool.
using your notes, all notes, 11162 on 24,
Okay.
and the Wikipedia article on sphere packing. We'll be talking about some pretty famous mathematicians
Oh, yeah?
like Kepler and Gauss,
Mhm.
and also more recent breakthroughs by mathematicians like Maryna Viazovska. Plus, we'll also be looking at how sphere packing is used in things like coding theory. So to start off,
Yeah.
what is sphere packing?
Well, imagine that you're trying to fit as many oranges
Okay.
into a box as you can.
I can imagine that.
That's basically what sphere packing is. But instead of oranges, we're thinking about mathematically perfect spheres. And the box could be infinite space.
Okay.
The goal is to find arrangements for the spheres that take up the most space.
Okay.
This is known as packing density.
Bagging density.
Right. And it turns out that this seemingly easy problem
Yeah.
is actually related to other parts of math.
Interesting.
Physics and even engineering.
So it's like a three-dimensional puzzle
Exactly.
with some pretty big implications.
Yeah.
Our notes mention Johannes Kepler,
Oh, yeah.
the astronomer.
Right.
He seems to have made a pretty important conjecture about sphere packing
You did.
all the way back in 1611.
Kepler guessed that the densest way to pack spheres
Okay.
was the way you see oranges stacked at the grocery store
Yeah.
in a pyramid shape.
Okay.
This is called a close-packed arrangement.
Makes sense to me.
It does, and Kepler's intuition was right on, but it took centuries to actually prove his idea.
Centuries.
Yep.
Wow. So who figured it out after Kepler?
In the 19th century, Carl Friedrich Gauss,
Oh,
a mathematician.
Okay.
He made some real progress. He proved that two common structures, the face-centered cubic,
Mm-hmm.
or FCC,
FCC.
and the hexagonal close packing,
Okay.
or HCP,
ACP.
structures, were the densest out of all lattice packings.
So hold on.
Yeah.
What are lattice packings?
Think of a lattice as a grid. So
Okay.
in a lattice pack,
Okay.
the spheres are placed at specific spots on this grid.
Okay.
It's a very ordered way of packing spheres.
So Gauss showed that within these lattice packings,
Right.
the close-packed arrangements Kepler thought of
Yeah.
were the densest.
Yes. But proving Kepler's conjecture for all arrangements, even the ones that are not arranged on a grid, was much more difficult.
Yeah.
It wasn't until 1998 when Thomas Hales finally proved it
Wow.
using a computer.
It sounds like proving that was a long process.
It was.
Now, one thing I found interesting in the notes
Yeah.
was this idea of jammed packings.
Oh, yeah.
What are those?
Jammed packings are where things get interesting. Instead of being perfectly ordered,
Mm-hmm.
the spheres get locked into less regular configurations, sometimes with really low density.
Wait, less
Eh.
dense. I would think that things crammed together randomly would make them more compact.
Not always. For example, there's something called the tunneled FCC crystal. It's based on the normal dense FCC structure, but it has these voids and channels that run through it,
Oh.
kind of like a sponge. This makes it have a low density.
So even with a structure that's based on efficient packing,
Right.
you could still end up with a lot of empty space.
It can.
That's really counterintuitive.
It is.
And then there are random packings
Yeah.
where the spheres are arranged even less orderly.
Even in these seemingly random configurations,
Mm-hmm.
there are still limits to how densely they can pack.
So there's like a hidden order
Exactly.
within the chaos.
There are rules that control how well spheres can fill a space, even in random arrangements. And these rules help us understand things like granular materials in the real world.
This is all pretty mind-bending.
It is.
Our notes also mention sphere packing in higher dimensions.
Oh, yeah.
I can barely imagine 3 dimensions,
I know, right?
let alone 4 or 5 or more.
That's where sphere packing gets really wild. In higher dimensions,
Yeah.
we're dealing with hyperspheres.
Hyperspheres.
Right? These are objects that are impossible for us to picture,
Uh-huh.
but they exist in math.
So how do you even begin to pack something
Right.
that you can't even visualize?
It takes some pretty advanced math
Okay.
and a lot of abstract thinking.
I can imagine.
What's really cool is that the most dense packings
Yeah.
in higher dimensions
Yeah.
often don't look neat and orderly to us.
Really?
Yeah.
So something that seems like a jumbled mess
Right.
to us in 3 dimensions
Exactly.
could actually be a really efficient packing in a higher dimension.
Exactly.
Our notes mention a mathematician named Maryna Viazovska.
Oh, yeah. She's amazing.
She made some big discoveries in this area.
She did in 2016. Viazovska figured out the best way to pack hyperspheres
Yeah.
in 8 dimensions. using something called the E8 lattice.
The E8 lattice.
Yes.
What's that?
Imagine a grid, but in 8 dimensions.
Okay.
The E8 lattice is a specific way of arranging points on this grid. It's extremely symmetrical. This symmetry makes it perfect for packing hyperspheres.
So it's not just about randomly shoving spheres together.
Yeah.
There's a real art to it.
There is?
You have to find specific patterns
Yeah.
and arrangements that work best.
A little while after her work on the E8 lattice, Viazovska and her team also solved the packing problem in 24 dimensions.
Wow.
They proved that the Leech lattice was the best way to arrange spheres in that dimension.
Okay, the Leech lattice.
Yep.
Another pretty complex idea, I'm guessing.
The Leech lattice is even more amazing than the E8 lattice.
Okay.
It has 196,560 points in 24-dimensional space.
Wow.
It's also very symmetrical, and it connects to other areas of math.
Like what?
Like coding theory.
Hold on.
Yeah.
Sphere packing is connected to coding theory.
Believe it or not, they are.
Wow.
It turns out that the centers of spheres in certain packings can be thought of as code words in a code.
Okay.
And the distance between these spheres tells us how good the code is at correcting errors.
So the way we send texts and download files is influenced by the math of sphere packing.
In a way, yes.
That's amazing.
It is pretty cool.
We've gone from stacking oranges to higher dimensions and error-correcting codes, all because of this seemingly simple problem of how to pack spheres.
It just goes to show that even seemingly simple problems can lead to some really complex and important ideas.
Absolutely.
Welcome back to our deep dive into sphere packing.
Okay.
So in this part, we'll take a closer look at some different types of sphere packings.
Sounds good.
Yeah.
I'm curious about the close packed structures we talked about before.
Oh, yeah.
Like FCC and HCP. What makes them so special?
They're pretty amazing.
Yeah.
Both FCC and HCP have a packing density of about 74%.
Wow. So they fill up almost 3/4 of the available space with spheres. That's super efficient.
It is.
Can you remind me what makes them so good at filling space?
Sure. Their efficiency comes from how they're stacked. Imagine a layer of spheres arranged in a square lattice.
Like a tray of oranges at the store.
Yeah, like that. Now, in FCC, the next layer of spheres sits in the little dips that are formed by the first layer.
Makes sense.
And then the third layer is shifted.
Okay.
So that the spheres are right above the spheres in the first layer.
Okay.
This creates what we call an ABC-ABC pattern.
So each layer is kind of shifted a little.
Right.
Creating a repeating pattern.
Exactly.
Okay.
Now, HCCP is a little different. It also starts with a close-packed layer, but the next layers are placed right above the spaces of the previous layer. So it's more of an ABA pattern.
Okay, so both packings fit spheres in the gaps of the layers below.
Yes.
But with different patterns.
Right.
That's cool. And are these arrangements only theoretical?
Oh, no.
Or do they exist in real life, too?
We see them all the time.
Oh, cool. Where?
For instance, lots of metals, like gold and silver. They form FCC arrangements in their crystal structures.
So the way their atoms are arranged affects what the metal is like.
It does.
In real life.
Yep. This close packing makes them malleable and ductile.
Okay.
Which means they're easy to shape.
I see. So that's why we can make jewelry and stuff from gold.
Precisely. HCP is also common in metals, like zinc and magnesium. And the way the atoms are arranged affects how strong they are.
Interesting. It's amazing how this math concept affects the materials we use all the time.
Right. Now, let's talk about another important packing.
Okay.
The simple cubic lattice.
Oh, I remember seeing that in my chemistry textbook.
Yeah.
It's the one where the spheres are arranged in a simple grid, right?
Yep.
Each sphere has 6 neighbors.
Exactly. It's not as dense as FCC or HCP.
Okay.
It only has a packing density of about 52%.
So pretty good.
It is, but it's really important.
Well, why is that?
Because it's so simple.
Okay.
It helps us understand more complex structures.
So it's like a building block for other packings.
Exactly. It's also much easier to study and visualize
than something like FCC.
Right.
Now, let's go back to that tunneled FCC crystal we talked about before.
Okay.
The one with all the holes in it.
Right. That's a good example of how Even small changes within a type of packing can totally change the density.
Right.
The tunneled FCC crystal looks a lot like a sponge, and it has a density of only about 49%.
Okay, so less than the simple cubic lattice.
Even though it's based on the FCC structure.
It's crazy how much variety there is
There is.
in these different sphere packings.
There is.
Now,
Yeah.
let's move on to random packings, where things get a little less predictable.
They do.
How do we even make sense of random packings mathematically?
That's a good question. Even though each sphere's position is random,
Huh?
they all behave in a pretty consistent way.
What do you mean?
Well, when you pour spheres randomly into a container and then press them together, they reach a density of around 63.4%
Okay.
every time. This is called random close packing.
So even though it's random,
Right.
there's a certain density
There is.
that they always reach.
Yep.
That's fascinating.
It is.
And is this useful for anything?
Definitely. It helps us understand
Okay.
how things like sand or powders behave.
Okay, so like how sand packs on a beach.
Exactly.
Interesting.
It also has applications in materials science and things like that.
Wow, we've covered a lot.
We have
From ordered structures.
like FCC and HCP
Yeah.
to random packings.
With all sorts of densities in between.
Yeah.
I'm excited to see where we go next.
Well, in the last part of our deep dive,
Yeah.
we'll talk about how this problem
Okay.
extends into higher dimensions.
Welcome back to our deep dive
Back again
into sphere packing.
to wrap things up.
I'm ready for those higher dimensions.
Right.
Tell me about hyperspheres.
Get ready. It's going to get a little weird. We're going beyond 3 dimensions here.
All right, I'm following so far.
So in these higher dimensions,
Yeah.
does sphere packing get harder to figure out? It's kind of tricky.
Okay.
It gets more difficult and also way more interesting.
In what way?
Well, what looks neat and tidy to us in 3 dimensions
Yeah.
doesn't always work the same way
Okay.
when you go to higher dimensions.
Interesting. So what we think looks like a jumbled mess
Right.
in 3 dimensions might actually be a really efficient packing in a higher dimension.
Exactly.
This is where Maryna Viazovska's work comes in, right?
Oh, yeah, she's a rock star.
She figured out the best way to pack in higher dimensions.
She did. In 2016, Viazovska proved that the E8 lattice
The E8 lattice, okay.
is the densest possible packing of hyperspheres in 8 dimensions.
So what is the E8 lattice?
You not imagine a grid,
Yeah.
but in 8 dimensions,
Right.
the E8 lattice is a specific arrangement of points on that grid,
Okay.
and it's super symmetrical.
Symmetry keeps coming up.
It's really important for efficient sphere packing. And just a bit later, Viazovska and her team figured out the packing problem for 24 dimensions.
Wow. 24.
That's right. They proved that the Leech lattice is the best arrangement in that dimension.
Okay, the Leech lattice.
Yeah.
Is that also a symmetrical structure?
The Leech lattice is even more incredible
Wow.
than the E8 lattice.
In what way?
Well, it has 196,560 points
Wow.
in 24-dimensional space.
Okay.
It's also super symmetrical, and it's even connected to other areas of math,
Like what?
like coding theory.
Wait a second.
Yeah,
How are sphere packing and coding theory connected?
it's pretty cool.
Okay.
You can think of the centers of spheres in certain packings
Mhm.
as code words in a code,
Yeah.
and how far apart the spheres are
Okay.
tells us how good that code is at fixing errors.
So the math of sphere packing helps us
Yeah.
send text and download files.
In a way, yes,
It's amazing how this abstract math problem
it is.
has such real-world uses.
And we've only just scratched the surface.
What do you mean?
Well, there's still so much we don't know about sphere packing,
Like what?
like packing in even higher dimensions.
Okay.
Or with different size spheres.
Uh-huh.
And even in curved spaces.
Curved spaces. Wow. This deep dive has been amazing.
It has.
We've come a long way
We have.
from stacking oranges
To hyperspheres.
and all this cool math along the way.
It shows you how a simple idea can lead to some big discoveries.
Definitely.
No.
Thanks for guiding me through it all.
I'm happy to do it.
And to our listeners, keep those spheres rolling.